Okay guys, number 30, we have a 100 turn of a coil, and if you guys read the problem, we're gonna take out the important point, so we can use it to answer the number A of the connection between the magnetic field and time between 0 second and 4 seconds, and B to find an expression with the current formula of the induced current actually, and number C, evaluate the current from 1, 2, and 3 seconds. So first thing first, we have 100 turns, and we have a diameter of 0.04 meter. That means the radius equals 0.02 meter, and we have a resistance of 1 ohms, and the magnetic field formula is T minus 1/4 of T square. So first thing first, we need to know what is the magnetic field from 1 second till from 0 second till 4 seconds. So okay, when time equal 0, magnetic field is 0. When time equal to 1 second, magnetic field equal 1 minus 1/4, 1 square. Magnetic field is equal to okay, so that's mean we're gonna multiply by 4, and this 1/4, that's mean is multiplied by 1, so magnetic field is 3/4 Tesla. When time equal 2 seconds, we do the same thing. Magnetic field is equal to 1 Tesla. When time equal to 3 seconds, magnetic field is equal to 3/4 Tesla. And when time is 4 seconds, magnetic field equal 0 Tesla. So the graph will look like this: 1, 2, 3, 4. This is time in second. That's mean 1, 2, 3, 4, and this one is between 1 and 2. So when it's 0 is 0. When it's 1 is 3/4. So that means here. When it's 2 is 1. When it's 3 is 3/4, and when it's 4 is 0. So it's gonna look like this. This is in relation with the magnetic field and time. Okay, question number B. You need to find an expression for the induced current. So we know that magnetic field is equal to constant multiply number of turns multiplied by current divided by L. The length is equal number of turns multiplied by diameter. So magnetic field is equal number of turns multiplied by the current multiplied by number of turns and diameter. This one will cancel out, so the current here will equal to magnetic field multiplied by diameter divided by the constant. This is the first step. And then we grab the derivative of the volt, of the induced current. This is the formula of the volt EMF. That's mean the induction multiplied by derivative of the induced current multiplied by derivative of the time. So we're gonna replace derivative of current with this formula. That's mean the induced derivative of the induced of the voltage of the induction is just going to be equal to current multiplied by resistance equal minus the length. The length is equal to constant multiplied by the n square area divided by the length, and the length is number of turns divided by diameter multiplied by magnetic field multiplied by the diameter divided by the constant. So this one will cancel out, and one of the number of turns will cancel out. So the current actually this one is divided by derivative of time. So current will equal number of turns multiplied current is equal number of turns multiplied by the area multiplied by the magnetic field. We forgot to cancel the diameter divided by derivative of time. Divided by the resistance. Okay, so now this is the formula we can use for the induced current. For number C, we have to evaluate what's the current in 1, 2, and 3 seconds. So number C, when time is equal 1 second, what happened? We know that current is equal number of turns, that's 100. The area of the coil is P, radius of 0.02 square, multiply by derivative of, where are you, of the T minus 1/4 T square divided by derivative of time multiplied by 1 of ohms of resistance. So current is equal 100 multiplied by pi multiplied by 0.02 square. Derivative of time is going to be equal to 1 minus 1/4 multiplied by time. So the current in 1 second is going to be equal to 0.0628 amp. So we do the same thing when time equals to 2 seconds. The current is 0 amp. Follow the same steps at the beginning. When time is equal to 3 seconds, current is equal to minus 0.0628 amp.